Okay, this is a bungee jump problem, like you have on the homework. It's a great application of work energy theorem. So as you can see here, you plan to bungee jump off a 70-meter tall bridge using a 30-meter long cord that behaves like an ideal spring with a spring constant of 200 newtons per meter. So that meter got dropped off. Now you just want to touch the water below. You don't want to go flying into it too deep, and you don't want to end up above it. We're going to ignore air drag and the mass of the bungee and the additional rope. So simplify this pretty much. And we want to find out how much, this is the question, how much non-stretching rope must you add to the bungee cord if you have a mass of 80 kilograms? Well, I can see right now I forgot to add in the height of the bridge. No, it's there. The bridge is 70 meters tall. We need to know that. So I'm going to draw a before and after picture first. So you're up on a bridge. This is you before. You've got a bungee cord tied to you. And down below is the water. This Y is 70 meters high. And this Y is 0. That's where you want to end up. Your velocity up here is 0 if you're jumping off. The X of the spring, how much the spring is stretched, is 0. It's not involved. Then you fly down. You're going to have a couple things going on here. I'm going to use some colors. You're going to have the length of the cord there. The cord is going to stretch. I'm doing that in this pink color, which is kind of hard to tell. Cord's going to stretch. And then you've got to add some extra cord so that you fly into the water. All right, splash. So this, that's the length of the cord. This section here, from there to there, that's the stretch of the cord. And this, from the ground to there, that's the extra rope. Non-stretching rope is called static rope, FYI. Okay, so I'm going to call this L. I'm going to call this X. And what do you want to call the extra rope? R is for radius, L for length. I've already used the extra rope. I got to add, I don't know, D, R. I'm going to call it R. What the heck? We're going to call that R. Now, something I know about these things is that L plus X plus R is going to equal 70 meters. That's how they relate. All right, I know L is 30 already. X I don't know. R I got to find out, so I got to get X. I think X is involved in the spring, so springs have energy. Pretty sure I can calculate the X from the energy. So I think that's what I got to do. I know the L already. Got that. I got to find this X, and then I'll find the R. So let's use energy. If we do a little LOL diagram, kinetic, gravity, spring, work, we got a boatload of gravity energy at the beginning. Whoop. It's the man, it's me, it's you. You, the earth, and the spring. No friction, no air drag, nothing extra. So you start with lots of potential of gravity. You're touching the spring, the rope, but it's not stretched. Then at the end, your velocity is 0 and your y is 0. But you have an x. We got an x there. So kinetic, not there. Gravity, not there. Spring, that's present. Internal energy, no heat generated, we're saying. So all that energy goes into the spring. So that looks like a pretty simple setup. We've got all the gravity at the beginning, energy, will go all into the spring at the end. Okay? Doesn't seem that hard. Well, what do we got at the beginning here? We've got the mass, we've got G, we've got height initial, or Y initial. Our book uses Y. Y initial. And that's going to equal 1/2 kx squared. Oh yeah, this isn't bad at all. Alright, I got to find x. Do some algebra. I got that x is going to equal the square root of 2mgy over k. Alright, plug that in. 280, 9.8, 70, height of the k, 200. Alright, let's see if we can see my calculator. Clear all that junk out. And 2 times 80 times 9.8 times 70 divided by 200 all to the power of 0.5. 23.4265 meters. That's more significant digits than I actually have in the problem. I got like 1 in the problem, but I'm going to carry it out because that's not my final answer. That's x. Alright, and now I know that L plus x plus r equals 70. So r is going to be 70 minus L minus x. So 70 minus 30 minus 23.42 yada 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 75. Plug that in my calculator. 70 minus 30 minus that John. Boom. 16.6 meters r. We only did one significant figure, so r is like 17 meters. Would be like 20 meters really, but 17 meters. You know, maybe I do 16. I don't want to really hit the water hard. So there we go. That's how you do it. Applying work energy to bungee cords. Thanks for viewing.